Hello and welcome back to this Common Lisp tutorial series. I'm going to do things a little bit different now. I've started a new job. I'm teaching computer science, and so my schedule is going to be not quite as flexible as it was while I was furloughed. However, I got a request to explore functional programming in Common Lisp, and that's exactly what we're going to do. I'm going to start doing these functional programming Fridays. I'm not entirely sure that this is going to catch on, but I'm going to try. So happy FP Friday to y'all. We are going to try and focus on one particular aspect of functional programming per video. We're going to start today with the infamous map function. We're going to, in other videos, look at filter, reduce, using lambda functions, and generally what comes part and parcel with thinking about functional programming, thinking about higher order functions and all that jazz. And hopefully I'm going to try and demystify it somewhat. So, with nothing more ado, I've just started my new project here. It's just going to be FN for our functional programming stuff. Really, let's just get into it. Why waste time? So, the map function. Common Lisp has about 7 map functions as it turns out. So I hope you are here for the long haul. I'm going to set a timer just now so that we can actually see how long this is taking, and hopefully I won't take up like 45 minutes or an hour of your time. Hopefully this will just be nice and simple. So if you don't know, the map function it's a way of transforming a list of items from one thing to a list of items that's been transformed. And like with many things with Common Lisp, there is a generalized function. Then you've got a number of specialized functions that are related to it. And I think it's important to start with a generalized function, even if it's not necessarily the easiest place to start. So we're going to do that. I'm going to set up a little list here. We're just going to print this out. There we go. So that has evaluated our list. There we go. You can see that it's just printed out that 1, 2, 3, 4, and 5. Now, the generalized map function in Common Lisp. Typically, the map function takes a function as a parameter, so the function accepts a function object, and then it takes a list. Now, I'm not going to get too much into what functions are yet. There's a lot that we have to cover really, and a lot of it is all intermingled with one another. So just trust me on this. We're going to try and produce a string, and we're going to use the function car uppercase, and I'm going to change our list here. We're just going to say H E L L O, and we're just going to try and print that out so you can see it appearing here on the right. So let's just focus on this thing here. We've got this list L, which is a list of individual characters, and I'm going to lowercase that one. There we go. So this is a list of lowercase characters, remembering that the hash, backslash, and a letter is how Common Lisp represents a character. And all we're doing here with map is we're going to say we want to map over something, converting it into a string, and this is the function, remembering that we use the hash single quote to reference the name of a function, because Common Lisp is a Lisp 2 and variables go in one space and functions go in another. We will uppercase the character that comes in from list. So this is why we get a string here, because we're converting it to a string. You could just as easily have done this, and instead of getting a string, you can see that we have a list that is uppercased. So what map does is gives you a target sequence, I suppose. So you've got lists, vectors, strings, any sequence type, and you use it with a backtick, a single quote, not a backtick, a single quote here as a symbol, because we want to send to that sequence, and then we use a function lookup here for L. We could just as easily have had numbers here. And we're going to change this to the 1+ function. And that's not going to work because we can't convert to a string, but what we can do is a list. And we get 2, 3, 4, 5, and 6. So we're just taking a list and we're converting it into another list, but let's see if we can get to a vector. Yeah, there we go. So we've got a vector here. So we're converting a list to a vector, and we're using 1+ to increment each of the numbers. So that is the generalized map function. I can see a case where this would be useful occasionally if you are getting a list of characters and you want to map it into a string, or you want to do something with those letters. The impression I'm getting is because Common Lisp as a language gives you the tools that the language implementer is used to implement the language, map feels like a rather lower level function that you can use if you want to. However, there are other map functions we could use. For instance, here you can see that we still get 2, 3, 4, 5, 6 just by using mapcar and using the 1+ function here on the list. And this is a more specialized function because we want to use the car, the contents of the address register, on this list. So we're going to map across this list, getting the car every time. And that's an important distinction because there is a related function that does something similar but also kind of different, and it operates on the coder, the contents of the decrement register, although it's not called that, but we'll get to that later. So here a mapcar will always return a list, and you can use any function here that you like. Now we can also do something else here, just so I've been entirely thorough. So this is going to give us the squares. So we get 1, 4, 9, 16, and 25. So I'm going to briefly touch on lambda functions here. There's a lot more to them than what I'm going to talk about here. In fact, I'm going to use lambda functions in another video, I imagine. But a lambda function is a function without a name, and it is bound to a certain scope. So here we are using the hash single quote, and then we're binding this lambda function to the function call of mapcar. So because mapcar is a function that takes 2 arguments, we are declaring a function is the first value, and this is a function, not a function call. Although to be fair, it's a function call to the lambda. Yeah, it all gets a bit weird. Nevertheless, this is a function object, not a function call. So this gets bound to the first parameter of mapcar, and the list gets bound to the second, and every time we get one more off the top of L, so 1 comes in, it becomes x, and x times x is 1, 2 times itself is 2, and 3 times itself is 9, and you know, sorry, 2 times itself is 2, 2 times itself is 4. So that is how mapcar works. It's just a way of going over items, and we can do something else here. What else could we do? We could do the 1 plus thing here, but we wouldn't necessarily have to. We could cube them. You know, there's another example of cubing our numbers. So anything that you could do to build a function, but you don't necessarily need to use it anywhere outside of your code except here. You could just do hash single quote lambda, and then just fill out your function body here, and this function will be bound to the scope of mapcar while it's running in this context, and then it'll just go away. It'll be garbage collected, which is pretty cool. Now, there is a complement to mapcar, and we're going to get into this now. It's called maxi. And it is very similar to mapcar, in fact. However, you will notice that the output list here is exactly the same as the input list. Now, I need to do something here. Def parameter Now, I'm really hoping this will work. It won't, because it's not evaluated yet, so I need to evaluate that into my interpreter. There we go. Hopefully it will work now. So, yep. We still get 1, 2, 3, 4, 5 returned, but let's have a look at this. I need to inspect this variable. Right. Okay, fine, I'll just print it out then. So, we actually have the elements that we might have expected to have. So if we evaluate this, we've got 1, 8, 27, 64, 125, which is what we've got here. And what's happened is we've pushed each new element that is generated here onto this. So what mapc does is it does exactly the same as mapcar, except it doesn't accumulate the values, it doesn't store them, it doesn't return them when the function is done, it just returns the input list. Now if we had done nconc, maybe, or append even. Nope, that didn't work. What does append take? Rest and lists. Okay, not what I want. And let's just set that back to what it's supposed to be. And that doesn't do what I thought it would do either. Maybe if we concatenate. Nope. Nope. So we're just going to have to stick with push for the time being, because I'm always a little bit fuzzy on these functions for joining stuff. Although maybe. I doubt this will work. Nah, that wasn't going to work. Okay, 5. So let's just reevaluate that and rerun that. That's by the by on just what I was trying to do there. All we're seeing here is maxi still runs the lambda function for every item in the list. It just doesn't store the intermediary values, and it doesn't build up a list. It just returns that. So if you don't care about the side effects of mapping over these things, like maybe you're pushing something to a variable somewhere else, you can use maxi for this particular use case. I have not seen this used in many other languages before, so I'm a little bit unsure where you would use this. However, it does exist, and it's there if you want to use it. Which leads me to the complement to mapcar. Which is maplist. Now, something we might want to go back to. Oh, yeah, I understand why. I have. I'm going to need to give it a specialized function here. So let's think, what are we doing? Yeah, this looks about right. So, what we're doing here is map and the like. They can take more than one list, as it turns out, actually. So here, I'm going to put that to a list, just so we can see better. And what we're going to do is, because we're taking two lists, we need an X and a Y, because there will be an item from L and an item from M. And all I'm going to do is increment X and then increment Y. So this becomes 2 and 7, which is what we've got here. Then we're going to do 3 and 8 here, because we're adding 1 to it, which is what we get there, 4, 9, 5, 10, and 6 and 11. So it's worth noting that you can actually pass in multiple lists, and so long as the function that you pass in here can handle all of the values, which this is why it crashed earlier, is because 1 plus takes 1 argument, and I was trying to pass 2 in, so that failed. But that's why we know that, and it was a perfect opportunity to show why we can take multiple lists here. The reason I bring that up is the examples in the hyperspec for maplist. They actually show this working with multiple things here. So we're going to say 8, 9, and 10. We're just going to start here with L, apologies. And what maplist does is it starts the list as a whole, then it gets the coder, the contents of the decrement register. then it gets the contents of the decrement register of that, and of that, and of that, until no values remain. So remember that looking at this list L here, 2, 3, 4, and 5 is the contents of the decrement register, or the rest. This is the first, this is the rest, the cutter, the car, the cutter. Now, because everything is a list, and this is a sublist of the whole list, technically this is also the car of this list, which means this is the cutter of this list. Which means when we get the cutter, that cutter also has a car here, and a cutter here, and a car here, and a cutter here, and then it's out. So what maplist does is it takes each list as a whole and then iterates over them, getting smaller and smaller and smaller, getting the cutter of each cutter until no elements remain. And if that doesn't really make sense, value of x is not a number, okay, that is quite correct because it's getting a cutter, or it's getting a list, so we can't sum it. So all we're going to do is we're just going to return the item. So there we go. I'm just going to rerun that. There we go. So we actually get the whole list here. Then we get 4 items, then 3 items, and 2 items, then 1 item, and we're out. So if we expand this to include the second list, we evaluate that. We can see here that we get a pairing of 2 lists. So this was the first. We actually have 2 things here. So we've got this first list, which then contains this list and that list. Then we've got this second list, which contains that list and that list. Then we've got this third list, which contains this list and that list. Then we've got this fourth list, which only contains 2 elements each now. Then we've got the final list, containing only the final elements. Now, if I was to make this one just slightly longer to this one, where are we looking? Oh, that's interesting. Ah, yes. So here we stop because we've exhausted the first list. 5 is the last item. We don't continue and then get to the smaller list of just 11. We can't because there's nothing left in L. We've reached the shortest list and that's where it terminates. Now, I am not entirely sure I have found a use case for maplist, but nevertheless it's quite interesting. It complements mapcar, where you're getting the first element, or the contents of the address register. It is nice to know, because of the way Lisp operates, with lists being composed of const cells and lists being sublists of sublists of sublists, the fact that you can take full control and say, just give me each input list and map over it getting smaller. It's an interesting solution. Again, I've not found a use case, but my experience has been that the developers of Common Lisp, they were very much compromising all the existing Lisps at the time, but they put a lot of good things into this language, and I have to imagine that this is here because there is a use case for it. I just might not have found it yet, and I'm sure as I do more development, there will come a time eventually when I will hit a certain classification problem and go, maplist is what this problem was. Maplist was written to solve this problem, basically. Now, just like we saw with the previous functions, and mapcar and mapc, what we are going to do, I'm going to say push, I'm going to say this list. going to say data 2. Make sure that we've evaluated data 2. That did not work. Got 2 arguments but expected 1. What? Okay. Oh yeah, right. I see why, because it's a list. How am I going to do this? Let's have a wee think. Oh, I suppose I could just do this. Go. So you can see here that mapl, it returns the first input list and not the second. It's the same with mapc here. If you've got multiple lists, it only returns the first one. That's the way the language is specified. But you can see here that we were able to push all the elements into our second list here. You can see the side effects do take place. The function does run. It just returns the first input list here as a complement to mapc. So mapl is to maplist what mapc is to mapcar. And again, for the same reason I haven't quite found a use case for maplist, I've not found a use case for mapl, because it seems a very specific use case, but it does feel like it's there for completeness sake to give the programmer absolute power, which is cool. And there's a couple of other map functions that we've got, so we'll copy this. There we go. So mapcam, it uses a different kind of operator here. So let's actually just say x. I'm just going to use an identity function here. So we give it an element, it gives it to us back. Super simple function. So it gives us 5. Now the way mapcam is defined is, where did I write mapcam down? So instead of using a list, it uses, so these here, map list with this is similar to mapcar. So mapcar is just like an implementation of map, but it uses a list to build something up. And here with mapcam, we use a different function. Instead of list, we use nconc. Nconc. Yeah, this. So I'm going to try something here, and we're going to see exactly what nconc does. So it takes some lists. So we'll say 1, 2, 3, 4, 5. Okay, map. I have no idea if this is going to work. I'm just trying something here. Yeah, I wasn't expecting that to work. Nevertheless, nconc does it do? I'm not clear on what it does. Well, whatever. I will need to go and have a look in the hyperspec for that, which I am just going to do right now, because it is a little bit unclear to me what this is for. And don't worry, like, I know it seems a bit weird, I'm here supposedly teaching y'all, and I'm having to look stuff up, but it's a pretty big language spec, and you could never really remember everything, and I did. I swear to you, I did look this up, and I was not... Ah, yes, of course, yes, I remember now, I remember. Here we go, it joins lists together, that's what it's for. Ow, that was my fingers. So, when we use mapcam, when we get the items together, we are sort of accumulating them, so we get the last one here. So, let's see. Presumably then, if this is the case, okay, so we'll extend our thing here. Let's take a y, and we're going to simply return x and y. Again, I have no idea if this will work. There we go. Okay, so yeah, there we go. Let's try this with mapcar. There's the difference. So when mapcar is using a list to join these things together, where we get 1 and 6, 2 and 7, nconcatenate, which is what I can't say nconc, it sounds wrong in my mouth, so I'm saying nconcatenate. Mapcan will use this to actually build a single flattened list of the elements rather than a list of lists. So that's what the difference between mapcan and mapcar are. Now, to further confuse things even more, we have mapcom. So let's take this. And I'm just going to see if I can clear this, just so that we can see what we're doing. So our maplist, let's get this out of the way. Our maplist does what we saw before. It returns a list of lists. List of lists. Oh yeah, that's right. Where each subsequent list is the cutter of the previous one, and so on until there are no elements remaining. Now mapcon does something different, I believe. Yes, it has flattened it, just like mapcar has done. So where we had a list nested inside of a list, nested inside of a list, we've just got lists of lists here, and this is using nconcatenate to concatenate the values down into smaller ones. So this flattens it. So to recap, Map is a generalized map function where you tell it what structure, any type of sequence, list, vector, strings, any other sequence types, and you give it a function to do something with them, and then you pass in the lists, knowing that these can take arbitrary numbers of lists and they will run for as long as the shortest list is. Mapcar is a specialized version of map that will get you each element of a list in turn and will perform some function on each individual item and will return you the transformed list. Why have we got, and this is just an example of cubing, so let's get rid of that just to keep things simple. Maxi is very similar to mapcar, but it just returns the first input list. It still runs all of this, so you might want to pass something in here. This might be useful if you're working with streams, for example, and you want to transform one stream and push it into another stream. You know, you're converting a file or something like that. That would be a perfectly valid use case. Maplist will get subsequent lists, so we'll start with that, then give you that, then that, and finally that individual item, and again it terminates on the shortest list and stops. Mapl is to maplist what mapc is to mapcar, so again if you're working with a stream here, perhaps even if you're not opening stream to read, maybe you're just writing to a stream, you obviously might want to not care about what the return value is, you might just want to write it straight out to a file, so this is where you could use the mapl equivalent to maplist. Mapcam, as we saw, will instead of giving you a list of lists here, it will concatenate them and flatten the list down for you. And we can get rid of mapcar because we already looked at that. Same with maplist. Just to simplify it, and matcom is to mapl what mapcan is to mapcon is to maplist what mapcan is to mapcar. So there's a lot of relationships going on here with the functions, and I know that this is very theoretical and very dry, and I can only apologize for that, but you know, we're here at like just over 35 minutes already just looking at what these functions are and how to work with them. My professional opinion is I typically really only use mapcar. I have used a map if I'm wanting to convert a list of items into a string, so I could very easily do this. So let's say I've read something and it's just given me a bunch of letters. And I want to convert it into a string. Really all I'm doing is just writing an identity function, really. I'm sure there's an ID function somewhere in Common Lisp. But all this does is it's taking a list of items which just happen to be letters, and by virtue of returning the item, just an ID function, and passing it into a string, this map will take a list of items and turn them into the string because they're both sequences at the end of the day. So this is where I might use a map over a mapcar, because mapcar will infer that you're writing it direct to a list. I wonder what nconc will do with strings. This might not work. I'm just curious now. Yeah, I didn't think that would work. Oh, I've just killed my REPL. Oh, it's restarting now. It's coming back online, I think. Anyway, we're basically done here. It doesn't matter if my REPL comes back or not. But these are the map functions, and this is why functional programming is going to take a while, because I imagine we'll have to go back over these and find some practical use cases for them. But we'll get there. I'm not sure where we'll go in the next lesson, but I hope this was a good introduction to some of the things we're going to be touching in functional programming. It's a wonderful paradigm. Although I am very comfortable working with object orientation and languages like Python, I'm getting that with Common Lisp. I'm intrigued by the Common Lisp object system. I've not bought the book yet, but I'll get there. But functional programming is what I find most exciting. I prefer it as a paradigm. It's not the perfect paradigm, but it definitely helps you think about the nature of code and of computations, and that's never a bad thing. So, happy Friday, enjoy your weekend, and I will see you in the next video.